Hi, so this is going to be the last lab video for the term, but don't worry, you can go back and watch all of these lab videos as many times as you want indefinitely. The last lab is right here, lab 8. This one is, of course, available on campus for you to print out. It's called Titration of a Diprotic Base. So I'm going to cover the background theory on this, and then, as in the previous videos, we will move into the lab and do the experiment. And I will show you all the measurements and things as we go. And so, what do you know about acids and bases already? That is a good question. Most people know that acids, well, they have a direct experience with them. They are sour, and if they get on your skin, like in a cut, they can sting really bad, right? Or if they get in your eye, they sting really bad. But that's not just acids that would sting, of course. Bases do the same thing. Bases would sting on your skin and in your eyes, and that's, like soap. Soap is a good example of a common base that you would deal with all the time. Now, what we're going to do for the lab, though, of course, is combine acids and bases in what is known as a neutralization reaction. And in particular, we're going to do another titration like we did for the vitamin C lab. We did a titration. And this time we're going to do titrate a base using an acid of a known concentration. All right, so let's get right into it. The kind of the background idea in this lab is the idea of Tums tablets. Tums tablets. Well, what are Tums? Antacids, right? For acid indigestion. They are made out of calcium carbonate. The idea is how much stomach acid can one Tums tablet neutralize? That's kind of a background theme to this experiment. Now, Tums is made out of calcium carbonate, which is CaCO3, but the problem is it's not soluble in water. At least it's very lightly soluble, okay? And we want to neutralize a base that is in water. And if we put a Tums tablet in there, and even if we grind it up and put the powder of a Tums tablet into water, it still won't dissolve. So that gives us a bit of an extra issue to get around in order to analyze how much acid can one Tums tablet neutralize. If we want to analyze that very accurately, then we need it to dissolve in the water very efficiently or completely. All right, so instead of using calcium carbonate or a Tums tablet specifically, we are going to use sodium carbonate. Okay, sodium carbonate is a base as well. And in fact, if you look at the formula, the carbonate is the anion that has the base property of neutralizing an acid. And what that means commonly is that it reacts with an acidic proton. Okay, it grabs onto that, bonds with the acidic proton, and thereby neutralizes it. Okay, so sodium carbonate is water soluble. Okay, the anion or the cations here, they're kind of arbitrary with respect to the acid base or the basicity of the carbonate. It's going to be the same. All right. So what we're going to do for the experiment is get an equivalent amount of sodium carbonate that is found in a Tums tablet, or the amount of carbonate that is found in a Tums tablet. We're going to get that from sodium carbonate instead of from a Tums tablet. So how much carbonate or how much calcium carbonate is there in a Tums tablet? Well, there's 1,000 milligrams, or 1 gram. Okay, I'm not going to show all these calculations on the board here, but if you take 1 gram of calcium carbonate, 1 Tums tablet, and you use the formula weight of calcium carbonate to convert it to moles of calcium carbonate. And you say, well, I got that many moles of carbonate. 1 mole of carbonate for every mole of calcium carbonate, right? Well, if I got that many moles of carbonate, I need it to come from sodium carbonate instead of the Tums tablet. So I say, okay, I need that many moles of carbonate from sodium carbonate, so you got to use the the formula weight of sodium carbonate to convert that many moles of carbonate to grams of sodium carbonate. Now, if you do that, it comes out to be 1.06 grams. I'm just going to write it here. 1.06 grams of sodium carbonate will give you the same amount of carbonate as there is in 1 Tums tablet. All right? That's easy enough. Now, let's see here. What is the reaction that you're going to do in the lab? And also, what is the primary reaction that happens in your stomach if you take a Tums tablet? Well, it is the neutralization of the acid. The neutralization between the carbonate and the acid in the stomach. What kind of acid is in the stomach? Primarily, or essentially, it is hydrochloric acid. Okay? That's what we have. We're going to have sodium carbonate, and it's going to be dissolved in water, so I'm going to put AQ for aqueous, plus hydrochloric acid, which is also, of course, an aqueous solution. Now, in the lab, we are going to use a 0.5 molar solution of hydrochloric acid. And that is about 5 times more concentrated than your stomach acid. Okay, that's good to know because there's a bonus question in this lab that asks at the end of everything, at the end of the procedure and all of the calculations, there is a bonus question that says how many milliliters of stomach acid can 1 Tums tablet neutralize based on your experimental results. So you need to know simply that the acid that you're going to use, or that I'm going to use in the lab, is 5 times stronger, roughly, than typical stomach acid, or 5 times more concentrated. All right. What happens when we mix these two? Sodium carbonate plus hydrochloric acid. Well, they react completely. Okay. Hydrochloric acid is a strong acid. That means that it will 100% or very, very, completely react with all the available sodium carbonate until it's all gone or used up. It will completely consume each other. All right? And so whenever they do react, all that happens is on paper it looks like sodium gets displaced by a hydrogen, or they switch places. So the product then is sodium hydrogen carbonate, and that's still aqueous, plus sodium chloride, which is just good old salt, table salt. All right? Now, sodium hydrogen carbonate is still a base. And that's a weaker base, though, than the sodium. This is called sodium carbonate, just plain sodium carbonate. This is sodium bicarbonate, is what this is called, or sodium hydrogen carbonate. And so, this is stronger, but it's still considered a weak base, but it's a pretty strong weak base, okay? And this is also a weak base, and it's a good bit weaker than sodium carbonate. Now, this is the first neutralization reaction of the diprotic base. Okay, it's reacting with one acidic proton. The acidic proton is the hydrogen on the chloride right there. And after this first neutralization reaction is complete, you're left with a solution of sodium bicarbonate and sodium chloride. Sodium bicarbonate is commonly known as baking soda. The same stuff that you can buy in the store to make your biscuits get all puffy if you're baking. And of course, people use baking soda to purify the air if they put a box of it in your refrigerator, open it up, and for cleaning purposes and things like that. Now, sodium bicarbonate will react with a second unit of hydrochloric acid. Okay, so this is the second neutralization reaction. After the first one is complete, then the second neutralization reaction starts to occur, and it's all in water, so I guess I should keep my AQ right there and AQ right here. And after this second neutralization reaction occurs, you get a similar result where a proton takes the place of a sodium cation, and now we'll have H2CO3, and the sodium will come over here with the chloride and give you another unit of salt. Okay? And that's called, this product right here, H2CO3, is called carbonic acid. Carbonic acid is not very stable in water. Okay? As soon as it is formed, it will break apart into two different things. And if you look at this formula, you can kind of see what it might be. You take one of these oxygens and put it over here with these two hydrogens, and what do you get? H2O, good old liquid. That's L for liquid. And what are you left with? If you remove one oxygen, you're left with CO2. CO2, of course, is known as carbon dioxide. And carbon dioxide is a gas. So what does that tell you about the second neutralization reaction? It tells me, at least, that you're going to produce bubbles. Everybody likes bubbles, right? So that's going to be interesting or fun to see, is the bubbles that are given off in the second neutralization phase of the titration that we're going to do. Because again, we're going to titrate the carbonate carefully with a hydrochloric acid of a known concentration in order to figure out how much hydrochloric acid can be neutralized by a Tums tablet. Okay, if there's any questions on that, of course, email me or leave comments in the comment section for this video. Okay? Now, what are we going to do next here? Well, I like to always mention a little detail about this. It's kind of fascinating to me, and it's relevant to biology a fair bit, I suppose. And that's, of course, your respiration and your blood. Your blood is a buffered system. When it comes to acid-base chemistry, one of the common things that you learn about is buffers. And buffers are designed or formed or made, are called buffers because they buffer against changes in pH. I'm going to talk about pH a little bit more in a second, what it is, and we're going to be measuring pH a whole bunch in the lab, and then you're going to graph the pH on a titration curve for this experiment. It's all in the lab handout here that you're going to be working on. So blood is a buffered system, and buffers in chemistry means that they don't change their pH very easily. So it's buffered against changes in pH. And generally they consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. And when you combine those two things, weak acid and its conjugate base, you get something that is called a buffer. Why? Because if you add some acid to a solution that already has a base in there, conjugate base, it will be neutralized, and the pH won't change very much. If you add base to your buffer solution, it will be neutralized by the weak acid that's already in there, and the pH won't be changed very much. So it's buffered against changes in pH. And so the reason I'm mentioning that is because your blood is a buffer system, and what are the buffering components of your blood? Primarily, they are carbonic acid, that's the weak acid buffer, and typically in your blood it's held in the form of dissolved carbon dioxide. Okay, so carbon dioxide is a gas, but some of it stays in solution as dissolved gas, and then it can be in the form of carbonic acid. Okay? Or it can act as carbonic acid. Well, that's the weak acid. What is the conjugate base of carbonic acid? Well, that's what we started with right over here. Sodium bicarbonate. So your blood is a buffered system with the principal buffering agents of sodium bicarbonate, or baking soda in your blood, and carbonic acid. That's pretty good to know. What is even interesting, or relates, like I said, to biology in addition to talking about blood, is the idea of respiration and how you can neutralize excess acids. Whenever you're working out, you do a bunch of exercise, it's commonly known that the cells of your muscles release lactic acid in abundance whenever you do a lot of work. And that lactic acid gets released into your blood, and it would be, or could be, excess acid in your blood, which would change the pH of your blood. And that's not good. If the pH of your blood changes by just a couple of tenths, or more than a few tenths, you are in serious life-threatening danger, okay? It's called acidosis if your blood gets slightly acidic. What is it? Let me say this, and I'll come back to pH again. But neutral pH on the pH scale from 0 to 14, neutral pH is 7. Your blood is buffered to be right about 7.4. And if it changes by just a few tenths, you're going to be dangerous. If it goes down like to 7.1, you're in a state of acidosis. If it goes down more than that, you're in a state of near death, if not immediate death, because it is that sensitive of a system to pH. And so it's very important that these buffering components, the weak base and the carbonic acid, can be maintained to keep your blood pH stable. So if you're working and the lactic acid is produced into your bloodstream, how is that going to get neutralized? Well, it's an acid. Well, along comes sodium bicarbonate that is dissolved in your blood, and it will hit the lactic acid, and excess lactic acid will get neutralized, and this sodium bicarbonate will be converted to carbonic acid. And what can you do then at that point to get rid of excess carbonic acid in your blood? Well, your lungs can breathe it out, right? How can it breathe out carbon? Well, it's converted to carbon dioxide. And so when you work out, lactic acid is produced in the blood, and the blood neutralizes it from the buffering component, and carbonic acid is produced, which is immediately converted to carbon dioxide, and you breathe more, you exhale more. So that is pretty cool to know that it's all tied in with the chemistry to help to keep excess acid from building up in your blood, and therefore causing a pH change and acidosis. Of course, if your blood goes above 7.4, then you can be in a state of alkalosis, which is less common. Alkalosis, I've heard, typically is only caused by some kind of medications that you may have taken that cause too much base anions to build up in your bloodstream too rapidly. So that's not good at all either. So that's a side note that, like I said, I always like to mention that about the relevance of this reaction and how you can tie it in with some other areas of science. Okay. So next thing to talk about then is a little bit more specific with respect to pH and the titration process that you're going to be going through for this experiment. Okay? On the pH idea, there is a scale, a pH scale that you're going to learn about. And you may already know a fair bit about it, or at least the basics on it. pH is normally in the range, or considered to be from 0 to 14. And neutral is right in the middle. A neutral pH is reference to pure water at room temperature. Pure water that doesn't even have carbon dioxide dissolved in it. Because rain is naturally, rainwater or water that's been exposed to air, is naturally slightly acidic. Why? Because carbon dioxide gets dissolved in there, and like we said a second ago, it will be in the form, or it can act as carbonic acid, slightly acidic. But if it's pure water, meaning no carbon dioxide dissolved in it, nothing in it but H2O, then it has a pH of 7.00, right at room temperature. Okay, so that is the neutral mark. Well, if you go above 7 on the pH scale, it is a base. And if you go below 7 on the pH scale, it is an acid. And of course, hydrochloric acid is the one that we are going to be using. And as you read through the material for this chapter, you'll learn all about the definition of the acids. And proton donor is a Bronsted-Lowry definition of an acid. It's a proton donor. Okay, and then whenever we measure pH, it is actually measuring not really a proton, because in water you don't have free protons just floating around. The protons always get stuck to a water molecule, and they make what is known as the hydronium ion. Okay? The hydronium ion is actually what you measure when you're measuring the pH. And I'm just kind of thinking how much detail I should go into right now. Let's just go straight to the chart or the graph that you're going to be graphing and talk about the expected results. So if you take and you're able to measure the pH of a system and you graph it as it changes in time, or as it changes with the addition of a base, okay, so or an acid, with the addition of a base or an acid. So if we, that's what we're going to do in the lab. We're going to measure the pH, and we're going to say, well, how does it change as hydrochloric acid is added? And the solution that you're going to start with is sodium carbonate. So I'm going to mix sodium carbonate in water, and it's going to be a basic solution. So the pH will be somewhere up here around 11, above 7. So you say, okay, about, let's say right here is 7. If your pH starts at 7, starts at 11, and that's whenever you added zero amount of, well, hydrochloric acid. So I'm going to put volume add of HCl. Okay? So this is how much hydrochloric acid did you add to the sodium carbonate solution? Or did I add to it? Well, initially we add 0. Okay, we're going to start out with the aqueous sodium carbonate solution with no hydrochloric acid added. The pH should be around 11. Okay, and I'll measure this with a pH meter. All right, so let's say that I'm going to then add a little bit of hydrochloric acid to this solution. What would the pH change to? Okay, well, a little bit of acid won't neutralize all of the sodium carbonate, but it will neutralize some of it, so now you have a less concentrated solution of sodium carbonate, essentially. So that means that the pH will be a little bit lower. As you go from 7 to 0, that's the acid range on the pH scale, right? The lower on the pH, the more acidic the solution is. So we're going to go a little bit lower if we add a little bit of hydrochloric acid. Okay, and you add a little bit more, a little bit more, a little bit more. It continues to go a little bit lower, but you're still left with sodium carbonate in the solution you start with, and that's the strongest base in the solution, as long as there's some of it left. All right, but eventually you're going to add this hydrochloric acid, and it's going to neutralize all of the sodium carbonate. If all the sodium carbonate gets neutralized, well, suddenly you're going to be left with just a sodium bicarbonate solution. The sodium bicarbonate solution is a weaker base, a notably weaker base than the sodium carbonate that we'll start with. And so adding that acid, and then you get to a point where all the sodium carbonate is neutralized, and you add a little bit more acid, and suddenly it drops, and you're now left with a solution of sodium bicarbonate. And sodium bicarbonate has a lower pH because it's weaker. Okay? And let me put this 7 down a little bit lower here, just for, okay, so that's neutral right there. And so we're still in the alkaline region, or the base region on the pH scale. Just say that's the 7 coming across there. But we had this sudden drop in the pH right here, because that's when all of the sodium carbonate was used up, and now we are just left with a solution of sodium bicarbonate, which is still a base. And that sudden drop, halfway down that sudden drop in pH is called the first endpoint, or equivalence point. The first endpoint of the titration. That's when the first neutralization reaction is complete. Okay, all of the base has been neutralized by the acid, and so you've gotten to the first endpoint of the reaction. Okay, and then we are down here with a solution of just sodium bicarbonate, and it'll do the same thing. It'll slowly decrease as we add a little bit of acid, add a little bit more acid, amount is going up, and it slowly decreases, until what? Well, eventually you're going to neutralize all the sodium bicarbonate. And then all the base is gone. All the basic, notably basic species are gone. They're neutralized. So we can't be a pH above 7 anymore. So at that point, the pH is going to drop suddenly a second time. Suddenly and significantly drop at the point that all the sodium bicarbonate is neutralized. And that is called the second endpoint. Okay? So this would be the second endpoint. If there's any questions on that, please email me and or leave comments. And after the second endpoint, you're then going to be down with just a solution of sodium chloride, and if you keep on adding hydrochloric acid, then you're going to have a dilute solution of salt water and acid. Okay, so that's what would be down here. It would just go down indefinitely if you keep adding hydrochloric acid. It'll get more and more acidic, but that would be the end of the experiment after you've reached that second endpoint. Okay, and the goal is to precisely measure these pHs so we can graph this from experimental results, and to check if the endpoints occur at the expected value or the expected amount of hydrochloric acid. All right? And we can predict where these endpoints are simply by knowing the concentration of the sodium carbonate in the solution and the concentration of the acid that we're using to neutralize it with. Okay? And that's some of the calculations that are in the experiment here that I'll go through with you as we get to them in the experiment. All right? Well, let's see if there's anything else that I want to mention in here on the board before we go to the lab. I think that might cover it. So let's go ahead and head to the lab. So I'm here in the lab, and we need 0.5 molar hydrochloric acid. Well, all I had handy, well, actually we have several different concentrations handy, but I thought this one might be the most easily usable one, but it's the wrong concentration. 6 molar hydrochloric acid. That is approximately half strength of what is called concentrated hydrochloric acid, which is 12 molar, or a little bit higher, 12.1 or something. I'd have to double check, and there's a little bit of variation in that. It's not super precise, but what I thought this would be a good opportunity to show you guys is a dilution. It is one of the most fundamental chemistry lab skills, is how to dilute something to the right concentrations. So let's see how to do that on the board real quick, and then we'll come in here and do it. 6 molar concentration acid, or concentrated acid. Now I want to get it down to 5 molar. So how am I going to do this? Well, there's a simple formula that you should learn and love to use because it's so useful in not just everyday chemistry, but everywhere. Now, it is this. The concentration, I'll put a big C, concentration of the concentrated solution, that's just conc, C-O-N-C, times the volume of the concentrated solution, so those are just little subscripts, is equal to the concentration of the dilute solution, I'm just going to put DIL, times the volume of the dilute solution. That's the equation that is known as the dilution equation. It is commonly given in chemistry as, if your concentration unit is molarity, then it's a big capital M, and you could say M of the concentrated solution times the volume of the concentrated solution, little subscript C's right there, is equal to M of the dilute solution times the volume of the dilute solution, with little d's right there, right? That works pretty good, or sometimes it's given M1V1 is equal to M2V2, and those are little numbers, which is okay too. That sounds pretty nifty if you say it like that. M1V1 is equal to M2V2. Anyways, let's plug in our numbers and see how to use this equation. Now, the molarity of the concentrated solution is 6 molar, and the volume of the concentrated solution is, well, I don't know what the volume is, okay? I'm just going to leave it as VC times VC. All right, well, what is the molarity of the dilute solution? Well, we know we want it to be 0.5 molar. Okay, what is the volume of the dilute solution? Well, that depends on how much you want to make. I'm not sure how much I want to make. I thought I had a lot of jars of 0.5 molar hydrochloric acid already prepared in the lab, but it's easy to dilute it, and that's what I'm going to have to do here. And if I want to have enough to use later, then I might want to have a good bit. For the titration, we just need 50 milliliters of the acid. So I'm not going to dilute a ton, I don't think. I just want a convenient amount. And 100 milliliters is convenient, because then I can just use a 100 milliliter graduated cylinder, right? So let's put that. For my dilute volume is just 100 milliliters. Now, one important thing to keep in mind when you're using this equation is that you have to have the same concentration units on both sides of the equation, and then your volume units will come out to be the same. And vice versa. You have to have the same volume units, and then your concentration unit will come out to be the same. The reason is simply because what we want is, in this case, the volume. In order to solve for volume, we have to divide by the concentration. So you have the same units of concentration on both sides, the concentration units will cancel. So let's see. I'm going to solve for volume of the concentrated. How much of the concentrated solution do I need to use to get 100 milliliters of 0.5 molar acid? Well, we should suspect that it would take a little bit of that concentrated stuff and we dilute it to, 100 total. And all you got to do is solve for VC. You have 0.5 times 100 divided by the concentration of the concentrated solution, 6 molar. Of course, like I said, you have 0.5 molar divided by 6 molar, the molar units are going to cancel, and all you're going to have left is the milliliter units of the volume. So it's going to be 0.5 times 100 is 50. 50 divided by 6 is, let's see, just to give a little bit of precision, divided by 6 is 8.3. So I need 8.3 milliliters of the concentrated acid, the 6 molar acid. And I need to dilute that up to 100 total milliliters, and then I will have 0.5 molar acid. Let's do it. All right, let's see how this does here. 6 molar HCl. Going to put it into 8.3 milliliters total. This stuff is very mean. I don't want to get any of this on my fingers. It will burn. So let's fill it up to 8.3. I think that's pretty good. Okay, put the lid back on that acid. Here's the 8.3 milliliters. 100 milliliter graduated cylinder. Since that's all I want in total, put that in there. Okay. And now we need to fill up the 100 milliliter graduated cylinder. Have a little rinse. That seems good enough to me. Okay, now we got to mix that 0.5 molar hydrochloric acid. I'm just going to pour it back and forth a couple times to ensure thorough mixing. Alright, got that. Okay, now this bottle magically appeared. That's the sodium carbonate right there. Okay, sodium carbonate. That's what we need. Let's see if we can measure it on the scale. So we need 1.06 grams. See, we're on the step right here, measure out 1.06 grams of sodium carbonate. I already got my 200 milliliters of water. Okay. Zero out the way boat. No plastic dish. Let's see here. Well, that's too much. That'll do. That is good enough for me. 1.062. Alright, and then we dump it into our 200 milliliters. See, this is filling up to 200 milliliters on this side of the scale, so I'm going to dump this into 200 milliliters of water. No, wait a second. I wanted to show you guys a cool special effect. So let's add an indicator to this water first and watch what happens when I dump in the sodium carbonate. That'll be I'm kind of skipping ahead here. To step 11, it says to add bromocresol green. That's an indicator. Oh, I forgot to talk about indicators on the board. I'll have to go back and do that in a minute. It changes colors over certain pH ranges. Bromocresol green, or BCG. That's what it says to add first, but I'm not going to add this one first. Instead, I'm going to add the phenolphthalein first. That's the second indicator that is going to be used. And I'm going to add that first because it has the nifty little property of being colorless when it's a pH below 8.5 or so. And that means clear and just look like clear water. But when it gets to a pH above 8.5, well, that'll be what is neat to see, because when you pour the sodium carbonate into the water, its pH shoots up, and that'll cause some interesting color changes. Here is the 1% phenolphthalein solution, and I'm going to add in, all it takes is 1 or 2 drops. So I'm just going to go ahead and put in 2 drops so we get lots of pretty color whenever we see the color. 1, 2. Say 2 drops, 2 little drops in 200 milliliters of water. How can that be enough? Well, there's our sodium carbonate. Trusty glass stirring bar. Nothing. Looks like nothing, just plain water. Let's dump in the sodium carbonate. Get the idea? Now I just gotta stir it until this stuff is dissolved. I want to be sure that I get all that sodium carbonate out of this plastic weighing dish. So I'm just gonna pour some of this water in there to rinse all that into the beaker. So on your sheet here, just cross this out and put initial phenolphthalein color. Okay. Because that's what we had here. The initial color, well, I saw a pretty bright pink. Now, what do you think is going to happen when we add the bromochrysal green indicator to this solution? Well, the bromochrysal green has a color that is blue at a high pH, above about 5, and is yellow at a low pH, and it's green around 4. Okay, so this is a high pH solution, so we'd expect it to be blue, but blue plus pink makes what color? Well, I decided to make this happen on a stir plate here so we can get some fast effect with the fast stirring. Some instant color changes. I think that was pretty cool when we had the flash endpoint color change in the other lab on vitamin C. So let's do that again. Something like it at least. Alright. Bromochrysal green. Now it says in the directions to put in 2 squirts of this stuff because it takes more of this stuff to get a nice dark color than the phenolphthalein. So here's the first squirt. Let's see what it does. Ooh, yeah, that is blue. But, that's like too blue. I wanted it to be more pinky color. That like overcomes the pink color. That's not good. Because we need to see a double color change. So I'm going to go ahead and add another drop of phenolphthalein to make it darker pink from that. Bing, 1 drop. Tell a difference? Oh, a little bit. 2 drops. Yeah, that's getting pretty purplish now. Oh yeah, that's pretty purple. Man, I'm putting in a lot more phenol. Somebody must have diluted my phenolphthalein. I don't know, but it's taking more of it to make it purple than it normally would. Or should. But that's a pretty purple color. I don't know how well it shows up on your screen, but I can see it pretty nicely. Now I got a lot of indicator in there, and that can sometimes cause the endpoint, the visual endpoint, to be a little sluggish at least. But I think it'll work alright. Let's take a quick look at this calculation here. This is just showing the concentration of the sodium carbonate solution that we made. If we started with 1.06 grams of sodium carbonate, and its formula mass is 106 grams per mole, then you divide that by 106 grams per mole. Grams will cancel, and of course that'll give you 0.0100 moles of sodium carbonate. Right? Now the question is asking what is the concentration of the sodium carbonate solution that we just put into 200 milliliters of water. So we take, and then we can write it like this. Use square brackets to symbolize concentration, and say concentration in molarity is, of course, going to be 0.0100 moles of sodium carbonate divided by 200 milliliters, but we need it in liters in order for it to be molarity, so it would be 0.200 liters. So that would then come out to be 0.0500 moles per liter. That's the concentration of the sodium carbonate. Now, one reason for doing this calculation is to see how we use the moles of sodium carbonate to predict the amount of acid that it's going to take to reach the endpoints. So that's on the next page. So if you see on this step 18, it says moles of acid required will equal the moles of carbonate. That's because, as we showed on the reaction on the board, it's 1 mole of acid for every mole of carbonate, and at least that's to reach for the first neutralization reaction, and then the second neutralization reaction is another mole of carbonate. But for the first neutralization reaction, we just found that the moles of carbonate is 0.01, and keep some significant figures. Then the moles of hydrochloric acid required is also going to be 0.01, and that means it's all that we need to know next is the concentration of the acid in order to predict how many milliliters it will take to deliver the 0.01 moles of acid. The concentration of the acid, like we said in the classroom, and it's written right here, is 0.5 molarity. So the liters of hydrochloric acid required is going to be moles of HCl that we need, and we need 0.01 to match the moles of carbonate. So we need 0.01 moles of HCl, and we take that and divide it by the concentration of the hydrochloric acid, which is 0.50 moles per liter. Moles will cancel, and that'll leave us with the liters of hydrochloric acid predicted to reach the endpoint to neutralize this much carbonate. And what does that come out to be? 0.020. Let me keep one more significant figure if we want to, because this had 3 significant figures. How precise is that concentration of the acid? Is probably best just to say 2 significant figures if we're lucky. And that's liters. And then down here it says milliliters. And so 0.02 liters is the same as 20 milliliters. So that, again, that means the predicted value to get enough acid, which is 0.01 moles, to neutralize 0.01 moles of carbonate is 20 milliliters, because that's the concentration of the acid, and that's what it gives us, is 20 milliliters when we divide. Alright, so that's what we are going to put to the test. So then we got to fill our burette here with the hydrochloric acid. If you are sure that your burette is clean, then all you need to do is pour in the acid. Of course, you could go through the cleaning steps like we showed, or I think I showed in the ascorbic acid lab. Yes, I remember how to clean the burette with the solution that you're going to use. So this is the 0.5 molar hydrochloric acid that we just diluted from the 6 molar solution, and hopefully we have 2 significant figures on this concentration so that we'll get good results, agreeing with what the prediction is. So make sure the burette is closed at the stopper here by turning it perpendicular to the column, and then carefully pour in the acid with the funnel. This is the same burette that I used for the ascorbic acid lab, so I know it's in good working order, which helps to not have to recheck it and re-clean it. Alright, so I got the acid filled just past the 0 mark, or a fair little bit past the 0 mark. Got it past the 0 mark so that I can drain the tip and get it to be down to 0, or start at 0 exactly. So I'm just going to get a beaker right here, and I'm going to just kind of bounce the burette to get any bubbles out of the tip, and then get this to come exactly down to start on 0. All right. There, one drop brought me back up to exactly 0. And now the burette is pretty well ready to go. I just need to set it in place, and then we'll get started on the titration. Clamp it in place here. Okay. Need to put the beaker under there that has our sodium carbonate solution with the stirring bar. Can commence stirring. Okay, I wanted to make that a graphical connection for you as well as I can with what we just showed on the calculations, how we get 20 milliliters for our predicted endpoint. What that means is on this titration curve, pH is expected to decrease, and when we hit the 20 milliliter mark, that should be the endpoint ideally. So that's 20 milliliters right there if everything goes according to plan with our concentrations being accurate. And that'll be 20 milliliters to hit the first endpoint, and we should also tie in the indicators and how they fit on this chart. The indicators will have a certain color at 1 pH, say phenolphthalein is at a high pH, like above 8 or so, it's pink. Okay? And so it'll stay pink all through this range, and then it'll turn colorless. So down here, phenolphthalein goes from pink, and then it goes to colorless. And so when you get to the pH right here, right around 8 or lower, say this is about 8, again, it's going to be colors, and then we'll just see a blue because BCG is blue at a high pH above, well, 5 or 4.5 or something like that. And then when you come down here to this endpoint right here, well, BCG is expected to be, well, it turns to its acidic color. Its acidic color is yellow, so BCG goes to yellow. So that would be when we hit the endpoint right here and it changes this big pH range for the second endpoint, it should change colors a second time and give us yellow. And not only that, if you remember at the second neutralization reaction, at the end we get carbonic acid. So that means that we should also get bubbles during this phase of the titration. As the carbonic acid is formed, we'll get more and more bubbles forming. That's this expectation. Now, when do you think this second endpoint is supposed to be? The second endpoint, well, if it took 20 milliliters to reach the first endpoint, then we made that amount of sodium carbonate. All of the sodium carbonate was converted to sodium bicarbonate, right? 0.01 moles of sodium carbonate gets converted to 0.01 moles of sodium bicarbonate. Well, how many moles of acid will it take to neutralize 0.01 moles of sodium bicarbonate? It'll take another 0.01 moles of acid. So that means the acid concentration is always the same, 0.5, and if you take the second round of 0.01 mole acid needed, it'll take an additional 20 milliliters of the acid. This is a prediction. So the second endpoint should be right here at 40 milliliters. Okay? And that's where we should see the second change in pH. Change in indicator color and a large change in pH. And I have yet to show you the pH meter. So let's go see the pH meter and the setup, and then we'll go through the final data gathering. Here is my fancy smancy pH meter. Now, this is the meter, and this is the probe. And on the tip of the probe, I have it in this storage solution to keep the probe in prime working order. Keeps it nice and clean and protected. And this is a handy pH meter. You don't have to worry about it getting messed up too easily because it's got this plastic casing around it. The actual measuring part of it is this glass bulb right there. It has a tiny little electrode in there that is going to detect or participate in detecting voltage changes that are due to hydronium ions, or hydrogen, you could say protons, but hydronium ions going through the glass, porous glass bulb or membrane right there. That's going to change the voltage inside the meter or inside the probe and go to the meter to give us a pH reading. Now it's an acidic storage solution, so you see the pH right here is starting out at 3.56. So I need to rinse that off in some nice water. Now in your directions, this is just water that I'm rinsing it in. It's got a little yellowish tinge from the old pipes underneath our building. Anytime we go for a long period without using the water in the lab, we can expect to get this lovely color water out of our old pipes under this building. But you know, it's still perfectly safe. You know, I filter my water at home too, so I would filter this stuff as well through a regular filter, you know, water pitcher filter or something. Anyways, what I was saying is, in your directions, it says to calibrate your pH meter. And that's using a typical handheld little pH meter that I have for my classes. This one isn't the one that I use for my classes. This one's a little bit fancier, and it's already nice and primed and calibrated and ready to go since I've had it in that storage solution to keep it in excellent condition while it's not being used. But let me show you real quick the typical handheld pH meters and what it means by calibrating those. So this is the typical handheld pH meter that I would have class use. It's similar to the other one. It's just all in one little meter with little batteries on it. So we don't have to have a separate little readout here or a separate little device. Anyways, these meters typically need to be soaked in water for a couple hours to prime the little glass bulb that's up in there, the glass membrane. And so I didn't want to take all the time to do that. And then you have to calibrate them or check the calibration much more carefully or routinely. And you would do that by dipping the tip into a buffer solution of known concentration or known pH. So those are manufactured, and you can buy them readily from supply companies. And I get one of a buffer 10, and then you dip it in there and you would turn this little screw until the readout said exactly 7.00 when you had it dipped into or immersed in the buffer 7 solution. Did I say buffer 10? Anyways, buffer 7, and you turn that little screw right there until it reads exactly 7. And then you'd rinse it off, and then you'd dip it into a second buffer solution that is either a pH of 4 or 10, and I would use a pH of 10 since our solution that we're going to be titrating right here is expected to start around a pH of 11. So we would calibrate around a pH of 10 using a second buffer solution that is manufactured to have exactly a 10 pH, and then you would dip the tip into that second buffer solution and then turn this little screw until this reads exactly 10 to agree with what the known pH of the calibration solution is. So that's a quick rundown of how to calibrate your pH meter if that's what you need to do, which is normally what I would have my classes do. Anyhow, let's get to the experiment. Oops, this thing got turned off automatically here. Okay, so as we go through this titration, you can see on your data sheets here that we need to fill in the values on the table, experimental pHs, color of the indicator, any other observations worth mentioning in this column. This column doesn't have to be completely filled with observations, just like, oh, I see bubbles in this range. Oh, the something something happened, and whatever seems relevant in there. So notice that the pH on the pH meter went up to 6.65 since it's just resting in water. I rinsed off that acid storage solution. All right. So I'm going to put it into our solution, and we're going to start the titration here in a jiffy. Now this pH meter can just sit in there the whole time that we're doing the experiment or adding the acid. I'm going to turn up the stir bar here. Don't particularly want the acid to directly hit the pH meter. That can make the pH jump around a little bit too crazy, perhaps. So I'm just going to make sure that it's not going to directly hit it. All right. So the initial pH is, well, hey, looks like I was pretty good on my prediction. It's 10.65. So I just write that down on the data sheet, of course, for the experimental pH at 0. I think there's also a place back in the procedures here. So you can write in the color that it starts out right here. It's, purple color. And then down here, the initial pH is 10.65. So you can write it on step 14 as well. And, like I said, have it on your data table, 10.65. And also write in your indicator color on that and any other comments that seem worth making. Okay, now the next volume to add. Next volume is 5 milliliters, and then 10, 15, and then when it gets close to 20, I make the volumes a little closer together so we can get that steep drop, or expected steep drop in the pH carefully graphed, and then it goes back to 5 milliliters at a time. And so I'm going to go through each of these total volumes and make the measurements, write down the measurements as we get to them. All right, so let's see. I'm going to open this up and go down to 5. You can see the pH is starting to drop already. Only added 2.5 milliliters about. Whoa, don't want to go too far. Not going to show you guys this the whole time. It's too hard to get it to focus on there. You can see that's a little over 3 milliliters. Remember, we go from the measure from the top down. So 3 is right up here, 3.1, 3.2, 3.3. So we just measure from the top down until it gets to 5. And then we write down the pH at that point, etc. So crank up the stirring a little bit so we get fast changes in our pH. But we don't want any splashing with the stirring. All right, so let me go down to 5. And there. That's 5 milliliters. And our oh, there we go. So it's 10.13 at 5 milliliters. So write that one down. Now we're going to go down to 10. All right, going down, down, down we are, almost to 10, 9, 9.5, and 10. All right, well that's pretty good on 10 milliliters right there, and the pH goes down to 9.65. Okay. Next volume on the data table is 15, so let's go down to 15. 11, 12, 13, 14 and a half, and 15. There we go. That's 15 milliliters of hydrochloric acid added, and the pH looks like it's stabilizing at 8 point. Ooh, it's not stabilizing still. What's it going to stop at? When you get close to the end point, as you should observe on that titration curve, the pH starts to change more rapidly and drastically, so it's harder to get a stable value. So that's why it takes a little bit longer as you get closer to it for it to stabilize. And it's looking like it's going to stabilize at 8.6. I'm taking 8.62. All right, 8.62. The next volume is 18 milliliters. So let's go down to 18 milliliters. Oh, let's take 8.60. Okay. Now let's go down to 18 milliliters. There's 16, 17, and 18. Okay, folks, this color is definitely looking lighter blue to me. I hope you were observing that color. I wasn't talking about the color here, which would have been good for me to observe more of, but the color was pretty well unchanged. Let me go back and watch the video real quick and see how much the color was changing. Okay, so at 18 milliliters of acid, the color has definitely gone from purple to blue. You can clearly see that in the video. I just double checked it. That means that we already hit the end point, basically, which is sooner than expected. And the pH is stabilized at 7.11. That's sooner than expected. Remember, we were expecting to be at 20. What does that actually mean? It means that our acid is probably slightly more concentrated than 0.5 moles per liter. So it doesn't take as much to hit the end point as predicted, because we measured out that mass of that sodium carbonate, and that stuff is pretty decently pure. Okay, but all we can do is carry on now, and our endpoint came a little bit sooner than expected. Another thing, though, that we can mention real quickly, remember on the board a minute ago, we said that it would take about 20 milliliters to reach the first endpoint, and an additional 20 milliliters to reach the second endpoint, so that's 40 total. Well, since it only took 18 to reach the first endpoint, we can predict that it takes 36 to reach the second endpoint rather than 40. So we'll put that to the test. After 18 comes 20. I'm going to go ahead and keep to the values on the chart here. So I'm going to go down to 20 next. Okay, there's 19 and 20. All right, so there's 20, and the pH is what? 6.8. Man, it's going down already. The bromocresol green doesn't change colors until I think a pH of 4.5, between 5 and 4. So actually, at 20 milliliters, it's already all the way down to 6.78. So I definitely think our acid is more concentrated than expected, or than intended, because it just wasn't measured very carefully for the starting 6 molar solution, perhaps. Okay, well, anyhow, let's keep going to 22 next. Okay, so it's holding steady. At 22, it didn't change a whole lot. It's only down to 6.6. 6.60 is going to go down a little farther. Let's pick up the stirring a little bit, see if that'll help it to equilibrate faster. So 6.5. I'm going to take 6.55. Oh, 6.54, fine. Then let's go down to 25 next. Bing. There's 25. Notice that the pH hasn't changed a whole lot. That's because we're not too close to the end point yet, so the pH changes very slowly. We're in a buffer zone. 6.2, looks like 6.28, 27. Oh goodness, 6.26. Okay, I'm taking it. Now we got to go down to 30. All right, 30 down to 30. Now prediction is that the next endpoint will come at 36, right? So we shouldn't hit the endpoint when we go down to 30. And we know that we hadn't hit the endpoint because, well, it's still blue. So there's 30 more milliliters of the acid added. Still nice and blue. Guess what I see in there? You see some sparkly looking little bubbles? Yep, I see some sparkly bubbles. That means carbonic acid was being formed. And the pH has gone down to 5.75. Man, we're getting kind of close to that expected change for BCG. So let's see if it happens at 35 or before 35. It shouldn't happen before 35. So I'm going to go down to 35 now. 32, 33, 34. Uh-oh. I see some color change happening and lots of bubbles. Lots of bubbles and some slight color change. That means that we are very near to the second endpoint. There's a little extra lighting right there. So I actually didn't go all the way down to 35 either. I went down to 34. So let's go ahead and mark out 35 and try to map this endpoint a little bit more carefully on the graph and say, instead of 35, put 34 milliliters. And the pH is 4.93. Okay, now I'm going to go down to 35 milliliters. See how that does. Oh my goodness. Holy moly. Ah. So, at 35 milliliters, we have hit the endpoint. And the pH is 3.67 and the color is yellow. So be sure to write down all the observations of colors, and I see lots of bubbles in there. And hopefully you saw a lot of bubbles too. So be sure to write those down at the corresponding values on your chart. And now 3.65 for the pH. And again, you can just mark out on the chart here, put 35 and 34. We kind of got those 2 points close together. And then we can go to 40 next. 40 we are. Okay. That is just a dilute solution of hydrochloric acid. And its pH is 1.96 or so. So we have hit the endpoint and passed it now. So we could say that the experiment is done and just graph those values. Let's go ahead and do one more value at 42. 42, and the pH is at 1.81. Alright, just dealing with the dilute solution of acid now. And that's the experiment right there, folks. So all you need to do next is take all these two columns of data and of course fill in your indicator color observations and bubbles and stuff, and take those and put them on your graph. Alright, put them on the graph. It should come out to look something like what we drew on the board, but of course we were off on the endpoints here. Mention that you can see that the endpoint happened between, again, I think it was between 15 and 20, and we don't know where. I said it was 18, but it must have been before 18 even, because this endpoint didn't happen at 36, which is double 18. It happened between 34 and 35, so which would be double 17 or so. And so that's the second endpoint right in there. Okay, so that's everything. So I hope you enjoyed this video. Hope you learned a lot. And perhaps I'll hear from you in the future. Good luck with everything.